afternoon, everyone. My name is Gal Oshri. I'm a product manager at AWS on the SageMaker team. I'm here with Sam.
Good afternoon, everyone. My name is Sam Palani. I'm a principal machine learning specialist here at AWS. I've been with AWS for around 4 years now, and my focus areas are natural language processing, distributed training, and responsible AI.
Awesome, and we're here to talk to you about training ML models at scale with SageMaker Training. Maybe before we get started, really quick show of hands. How many of you are already training machine learning models today? Awesome, and are any of you training models that are taking longer than, let's say, 4 hours to train? Awesome, yeah, so you'll benefit from some of the sections in this talk about large-scale training and distributed training. So today we'll talk about the AI/ML landscape at AWS, training ML models at scale on SageMaker, large-scale training, hyperparameter tuning, and we'll wrap it up. And I want to start the talk by just giving you a sense of when I started training deep learning models back in 2017, I just wanted to kind of start using TensorFlow and Keras to try and do some architecture search, some hyperparameter tuning, and just get a feel for what it's like to train neural network models. And back then, I had to provision a cloud instance with GPUs because I wanted to accelerate my training. I wanted to install all the NVIDIA drivers, CUDA, get everything working with the frameworks, make sure the GPU was training the model, and so on. And that took an entire afternoon. Only in the evening, I was able to actually start playing around with the hyperparameters, changing the layers in the network, which was really the part that I wanted to focus on. So I had to do all this work to get ready, which felt productive and difficult, but that wasn't really the thing that was my goal. So I'm excited to talk today about how AWS really helps with removing that undifferentiated heavy lifting that you have to do to set up with machine learning and to get started before you can do all of the actual critical work that you want to do as a machine learning engineer or data scientist. So at AWS, we think about 3 layers for ML products. The first is the ML frameworks and infrastructure, where you have things like the DL AMIs to enable you to use frameworks like TensorFlow and PyTorch really easily, or you can bring in your own frameworks. You can use instances like the P4D, which provide 8 NVIDIA A100 GPUs to enable training machine learning models at the largest scale with top performance. Or you have EFA, Elastic Fabric Adapter, that let you have really good communication between the instances, which is very important for large-scale distributed training. In the middle layer, we have SageMaker, which makes it easy for any data scientist to build, train, and deploy machine learning models. It provides products like Data Wrangler that helps you prepare data, SageMaker Training that helps you train models, and that's what we'll focus on today. But it also has notebooks for quick experimentation and inference to allow you to deploy your models and get an API that you can use to get predictions from that model. And all of these things are available within the SageMaker Studio IDE that provides a single pane of glass for the entire ML workflow. And just last reInvent, SageMaker launched SageMaker Canvas that enables any business analyst or domain expert to train ML models without any ML expertise. And SageMaker Studio Lab that makes it really easy to get started with some learning and experimentation with a no-cost and no-setup environment. At the top layer, we have the AI services that make it possible for any engineer to take advantage of ML in their apps without any ML expertise. So you can use things like Transcribe to convert speech to text, or Amazon Personalize to add recommendations to your product seamlessly. But for today, I want to focus on SageMaker Training and the core concept behind it, which is the ephemeral cluster. So you can tell SageMaker Training, I want to train a particular model with this data set and using this cluster configuration. SageMaker will spin up that cluster, those instances, for you. It will download the data from S3. It will download the model from ECR, start the training, and during the training, it will log metrics to CloudWatch, or you can use other things like TensorBoard if that's what you prefer. And at the end of training, it will output the model and other artifacts back to S3 and spin down that cluster. And that last point is really important because if you're working with very expensive GPU instances, you don't want them to keep running when you're not training your model, right? You don't want to be wasteful. And obviously, this is an oversimplification. At each of these stages, there are many different options you can choose from, whether that's loading the data from EFS or FSX Luster instead of S3, or changing how you load the data. For example, you can download the data at the beginning of the job before the training begins, or you can stream the data during training, which is great if you have a very large data set and don't want to wait for it all to be downloaded before you begin. Again, there are many different ways to train the models on SageMaker. One of the simplest ways is to use the built-in algorithms. These offer you kind of a choice of around 17 algorithms where you can choose from things like k-means clustering, image classification, factorization machines, to train a model without writing any algorithm code. You just provide the data, choose the algorithm, and start the training job. Going one level deeper in terms of flexibility, we have script mode, where you can use one of the framework containers like TensorFlow or PyTorch and just provide the Python code that you want to use to run the training. So if you're already training models with PyTorch, let's say, on your laptop today, it's very easy to move that script and get it running on SageMaker. Another level down with more flexibility is bringing a Docker container that has all of the model code and frameworks and requirements that you want for training the model. So that's the full flexibility option. And we talked about training the models on the cloud, but you can also train them locally if you want to do some quick debugging or figure out something about how the SageMaker APIs work. So that's a good option to kind of get started and make sure that things are set up appropriately before you start training on the cloud. And lastly, in SageMaker, there are various ML ops tools to enable better integration of ML across the ML workflow and integrating it into your actual application. So for example, you can use SageMaker training within a SageMaker pipeline so that you do the training after some amount of data preparation is complete. And as soon as the model training is done, you can evaluate the model and deploy it if it meets the bar. Let's take a quick look at what the PyTorch estimator, the script mode that I mentioned, looks like in SageMaker training. So you'll see that I'm defining the PyTorch estimator. I'm providing an entry point, which is just the Python script that I would have used to train this model on my laptop. It defines the model, it defines the training loop, it outputs metrics, and so on. Then I define the instance type and instance count. In this case, I just choose one G5 instance that provides me an NVIDIA A10G GPU. But I can easily change the instance type to explore something else, or change the number of instances that I'm using to train the model. And Sam will talk about distributed training a bit later to show you how to really scale up that training. I then define the metrics. So my script outputs a loss periodically after every few steps. And by defining the regular expression here in this estimator API, I'm telling SageMaker I want to keep track of that metric in CloudWatch during the training. Finally, I call estimator.fit with the location of the data in S3. And I can start the training. And SageMaker will spin up the cluster, download the model, start training. I can then look at the AWS Console to view the training job and to see the status and how long the training has been going, whether anything has gone wrong. I can clone the job to tweak something about it, change maybe the instance type, and start again. And while I'm showing the UI here, everything is also available through APIs. And over here, we can see the loss in CloudWatch automatically provided to me by SageMaker, along with several other metrics not shown here, such as GPU, CPU, and memory utilization. So it's really easy to kind of get started and monitor these really important metrics while the job is progressing. If I want to do NLP, natural language processing, you might be familiar with Hugging Face, which provide a lot of tools and models to get started. You can either download an existing model and use it pre-trained in your app to start getting predictions, or you can train and fine-tune those models. And this is what we're showing here, where I'm taking the Distilbert-based uncased model from Hugging Face and using a very similar API to fine-tune and train that model in SageMaker. So the main differences here are that I've changed from the PyTorch estimator to the Hugging Face estimator, and I've pulled out the hyperparameters into a separate object so that I can easily modify them as part of my kind of training job creation, right? So now I can just repeat this and change the batch size, for example, to try out different things with the job. And especially as we get into NLP and larger models, thinking about the performance and optimizing the model is super important. You might think about changing instance types to ones that might be more powerful, or increasing the number of instances to scale up the training. Another option is to optimize the kernels or the operations within the model. And that's something that the SageMaker Training Compiler can help with, because these things are often extremely difficult to do and require a lot of domain expertise. So the Training Compiler, for example, can help you with things like graph optimization, to fuse ops together if it makes sense for the graph to be able to run more efficiently and faster. And I'll show on the next slide that it's really easy to add the Training Compiler to your estimator to take advantage of these benefits. And finally, the Training Compiler doesn't have any extra charge. So if it helps the training be faster, it automatically translates to cost reduction for you. So over here, you can see the exact same code we showed before with Hugging Face, but now we're importing the Training Compiler config and using that in the Hugging Face estimator. I'll now turn it over to Sam to talk about distributed training.
Thanks, Gal. So before we talk about distributed training, I just wanted to take a moment to check how many of you all use distributed training today. I'm trying to get a gauge. OK, that's fine. So let's see why we need distributed training, or what problem we are trying to solve with distributed training. So first are the data sets. If you look at the data sets, very popular data set, the ImageNet data set, I'm sure you all have used this a few times. This data set grew from 3.2 million images in 2009 with 5,000 categories. And fast forward to 2020, this actually grew to over 14 million images with over 21,000 categories. Now that's a huge increase. Now this is not just true with images. If you look at some popular text-based data sets, like the Squad data set, which is very common for NLP, even that grew by over 50% just in between versions. On the other end of the spectrum, models are getting more complex and larger in size as well. Now, Elmo, which was the state of art for NLP in 2016, had over 93 million parameters. Now, GPT-3, which is the current state of art, has over 175 billion parameters. Now, in the last couple of years, we've even had trillion parameter models like Megatron and all. But what does this all mean? Like, why do you care about the data size and the model size? Well, it turns out that machine learning and machine learning training in specific requires a lot of memory. But then why do you need the memory for? You have your hard disk and you have your storage. Why do you need the memory for? Well, you need memory to at least store your model, a subset of your training data set, and some temporary storage to hold your intermediate calculations. Now, while hardware manufacturers have done a great job in increasing GPU and CPU capacity year over year, the rate at which these data sets and models have grown has far outpaced this. So what do we do? So that's one of the primary reasons we go into distributed training. Now, if you look in the industry, there are a few different ways to do distributed training, but we'll focus on two more commonly used methods of distributed training across the industry. Again, not surprisingly, the two most commonly used methods are data and model parallel. I'll talk a little bit about this for a moment. And this is very generic. This is not specific to AWS, or this is not specific to SageMaker at all. The first one is data parallelism. The way data parallelism works is that the training data set is split across multiple nodes. Now, I use the word nodes and CPUs and GPUs very interchangeably. So when I'm talking about nodes, I typically mean a single CPU or a GPU. Each node or each GPU has a replica of the model. Each node then performs a forward and a backward pass operation over different batches of training data. It's important to remember that under this method, you're still required to fit your whole model and at least one training record into the memory. So if you have a model that is really large and cannot fit into the memory, you probably have to look at other options. Data parallelism alone might not work for you. Now, due to the distributed architecture, there are additional complexities involved with calculating and synchronizing the gradients under this method. Now, model parallelism, on the other hand, involves partitioning the model itself across multiple nodes or GPUs, where each GPU has a subset of your model layers. Now, let's pause there for a moment and double-click on this statement. Now, if you look at how a neural network works, data flows sequentially from one layer to another. That is, data passes from your input nodes through your hidden layers, the transformations are applied, and then passes out through your output layer and calculates the loss. And the same sequential happens in the reverse way when you do a backward pass and update the gradients. Now, there's a problem with this. If you go and randomly split your layers across multiple nodes, what would end up happening is that you will have one node doing all the processing while the other nodes are idle. And this is not something that we want, because GPUs are scarce resource, and we want them to be utilized as much as possible. So what do? So efficiency, when you build a pipeline parallel method, depends on an efficient pipeline execution schedule. And I'll talk a little bit more about the pipeline execution schedule as we move forward. Now, SageMaker has a couple of native libraries that allow you to do both data as well as model parallel. Primarily the SageMaker Data Parallel and the SageMaker Model Parallel library, or in short, DDP and SMP. Now, what this means is these native libraries take the heavy lifting of splitting your data or splitting the model for you, and they are also optimized for the AWS infrastructure. For example, a lot of resources in a distributed training goes or is consumed by the internode communication. Now, what we have done is we have optimized our software stack to work really efficiently with our hardware stack, which makes sure that this internode communication happens in a really efficient manner. And the result is that you get approximately 20 to 40% benefits compared to NCCL or traditional MPI-based solutions. Now, I'll go a little bit deeper into both these libraries and how they work behind the scenes. I'll start with the Data Parallel Library, or DDP for short. Now, the way the distributed data parallel library works is all the GPUs in your cluster are assigned ranks and are referenced as workers. The rank 0 in your training cluster is always your leader node. Now, the other important thing to remember over here is that, or for example, in this example, if you look at it, you have 2 instances with 4 GPUs each, and the GPUs over here are ranked from 0 to 7, like shown in this diagram over here. Now, if you've ever worked with deep learning, you're familiar with the concept of a mini batch. We take the same mini batch that you already use, but what we do is we take the mini batch and then we divide it by the number of nodes, and each of those nodes gets a subset of this mini batch, which we also refer to as micro batches, something like this. Now, the library is responsible for maintaining replicas of the model on each of those workers and also calculating the gradients. Once all the micro batches are processed, the library is responsible for synchronizing the weights from each of those workers into a single aggregated model. Now, I mentioned that you can use our native libraries, and this is how our native library works behind the scenes. I also mentioned that there are minimal code changes that you need, but there are still a few code changes that you do need to do. I'll show them. So there are 2 places where you need to do the code changes. One is during your training script, and the second place is when you're actually kickstarting your training job. You start by importing the SageMaker distributed training library. And this is an example of a PyTorch training script. But you can also find our TensorFlow examples on the SageMaker examples GitHub repository. So for the rest of the talk, I'll stick with all PyTorch examples. So you start by importing the SageMaker distributed data parallel or model parallel library. And within that, you import the PyTorch module for that. Next, we resize the batch size by dividing it by the number of nodes. Next, what we can do is we initialize we pin each of those GPUs to a local SageMaker library rank like so. You define and write your model as you normally would within PyTorch or TensorFlow. But then what you do is that since you have imported and initialized the library before, you just go ahead and wrap your model around the imported library. Now, you're probably also familiar with the data sampler. There's one additional change that you need to do with your data sampler by specifying the training data set, the number of replicas, as well as the rank. Finally, when you're ready, the last thing you need to do is make sure that you save your checkpoints as well as the model only on the leader node. In this case, as you remember, rank 0 is your leader node. Now, once your training script is ready, you're good to start or kick off your training job. You can run a SageMaker training job using one of our pre-built TensorFlow or PyTorch containers. Or alternatively, if you choose to bring your own container, you can do so by extending one of our publicly available deep learning containers, or DLCs for short. Now, if you remember from the previous slides, Gal talked about how you create an estimator. You go ahead and create an estimator the same way as you normally would, irrespective of whether you're using distributed training or not. But all you need to do is just add another parameter where you specify the distribution strategy as SM distributed data parallel within the estimator. Optionally, you can choose to specify any custom message passing interface options using the custom MPI options parameter if you choose to do so. Finally, when you're ready to start your training job, you call the fit method on the estimator and then pass in your training data set. That's all it is. So 2 places you need to do the code change. One is on your training script, and second is finally when you kick off your training job. I'll move on to the model parallel library. The SageMaker Model Parallel Library, or SMP for short, is another native inbuilt library from AWS specifically for distributed training. Now, large models that were previously difficult to train due to limitations of GPU can take advantage of model parallel. The SageMaker Model Parallel Library automatically partitions your model in a way that optimizes GPU utilization. It then sets up an execution pipeline to efficiently execute these partitions. Now, all this is fully managed for you within the SageMaker platform, and is also provides complete integration with popular deep learning frameworks such as TensorFlow or PyTorch, as you saw. Now, we also talked about the pipeline execution schedule. As I mentioned before, there are a couple of different ways you can execute the pipeline, and in the next couple of slides, I'll talk more about what the pipeline execution schedule is and what those different methods are. But for now, what I'll do is go behind the scenes on how model parallelism works within SMP. So when you kick a training job, or when you kickstart a training job with SageMaker Model Parallel, what the library does behind the scenes is it goes and analyzes the model training graph, along with analyzing the tensors using SageMaker Debugger. Now, once it analyzes this, it goes ahead and splits or partitions the model with a view of, one, maximizing the GPU utilization, And second, reducing the internode communication. Now, if you remember before, I talked about how important it is, or most of the processing that resources that gets consumed during a distributed training strategy is because of those internode communication. So we do two things. One is make sure that all your GPUs are fully utilized. And second, we make sure that the internode communication between those GPUs is as minimum or as optimized as possible. Now, once these partitions have been defined, we go ahead and place these partitions on different GPU devices and then set up the pipeline. That's stage number one. The second stage actually involves executing that partition, again with a view to stabilize the GPU execution. Now, similar to data parallel, the mini batch within your, as you define within your training script, is then further divided into n micro batches. Here there's a slight difference. N in this case is a hyperparameter that you decide. These mini batches are then sequentially fed into a pipeline, which is also decided by you, a pipeline strategy, and I'll talk a little bit more about pipeline strategy. But these micro batches are sequentially fed into this pipeline, but the execution is based on the library, the library makes a call based on runtime how to schedule these micro batches. What this means is that during any single forward or a backward pass operation, a same device, and a device in this case is a GPU, a same device might be visited more than once. For example, assume that within a micro batch, the beginning and the end operations could be placed on one device, whereas all the operations in between could be placed on a different device. In this scenario, what would happen is that the same device could be visited 2 times. Again, I have an animation here which will kind of make it a little bit easier to understand this. So if you look at this, the ultimate goal that we are trying to achieve is to make sure that we, as minimum, we can have the idle time for each of those GPUs. Again, minimizing the idle time for any of those GPUs. Now, we talked a lot about a pipeline execution schedule. I'll spend some time going a little deeper into what these pipeline execution schedules are. So before I get into the details, I just want to do some naming conventions over here. So the boxes in blue represent a forward pass operation. The boxes in orange or yellow, however the display is, represent a backward pass operation. Similarly, the letters F and B represent forward and backward pass operations respectively, and the numbers 0, 1, 2, 3, and so on represent individual micro batch identifiers. Now, there are 2 types of pipeline execution schedule, a simple and an interleaved schedule. SageMaker model parallel by default uses an interleaved schedule, so let's kind of look at that for a bit. During an interleaved schedule, all backward pass operations are prioritized as much as possible. Now, why do we do this? The main reason is that when you do a forward pass, what happens, as you all probably know, is that some memory is utilized and reserved for all your activation outputs, or the outputs from your activations. Now, prioritizing backward pass, now that memory is still reserved until the whole backward pass operation is complete. So even though a forward pass operation happens, the activation, each of those nodes are activated. The activations are stored in the GPU, but they are held in the GPU. So they are not freed up until the backward pass completes. So by prioritizing the backward pass operations, we free up those activations, resulting in a more efficient memory utilization straight away. In a steady state, what this would mean is that a device would alternate evenly between a forward and a backward pass operations. What this would also mean is that backward pass on a single or a specific micro batch could actually happen before the forward pass of another micro batch. For example, in this specific case, the backward pass of the B0 microbatch can actually happen before the forward pass of, say, the F2 microbatch. This is something new or slightly different from a traditional forward-backward pass mechanism that we do within any deep learning training. In contrast, what a simple execution does is that it prioritizes all the forward pass operations before moving to a backward pass operation. And that's basically, at a high level, how these pipeline execution schedule works. Again, to summarize this, SageMaker model parallel, by default, will use an interleave strategy, but you have an option of changing the strategy. There are certain scenarios. In most cases, we have seen that an interleave strategy will work with most models as well as most data sets. But if you have specific use cases where you're dealing with really small batch sizes, in those scenarios, you might want to experiment with a simple strategy and see whether you are able to achieve a shorter training time. Now, there's another area of large-scale machine learning that we wanted to cover today, which is called as hyperparameter tuning. Now, again, moving before I want to make this a little interactive. Do you all do hyperparameter tuning today? Yes. Can you also speak out? How do you do it? Yeah, that's one way. So why do we, like when we talk about hyperparameter tuning at scale, there are different ways to do it. But in essence, just so that we are all on the same page, let's actually say when I talk about hyperparameter tuning and when you talk about hyperparameter tuning, both of us are talking the same thing. So hyperparameter tuning, when we are talking about it, we start with a model and an objective metric that we are trying to optimize. For example, it could be your accuracy, it could be your F1 score, or whatever you're trying to optimize for. So you start with the model and the model features and the objective metric. You add certain maths to it, and then you try as much as you want. And then come to a convergence. Now, as you all know, there are a lot of commonly used methods for hyperparameter training. I heard someone call out grid search. Couldn't see because of the light blaring at my face. But yes, grid search is probably one of the most commonly used hyperparameter optimization approaches over here. So what does grid search do? So think of grid search as a virtual grid of all your hyperparameter value and combinations, where each cell in that grid contains a specific hyperparameter and its value. The way hyperparameter search algorithms work is that they traverse each grid one cell at a time, executing a training job with that specific hyperparameter and its value. Once you have completed traveling throughout the grid, you would have executed n number of training jobs based on the number of cells in the grid with each hyperparameter value. Or in summary, you would have executed all possible hyperparameter value combinations when you do grid search. Now, it's also very obvious that when you scale machine learning training, this is something that is not really possible in most cases. It's very expensive, and you probably, a grid search would probably take weeks or even months based on the size of your data set and the size of the model and your hyperparameter space. The other commonly used method is random search. And random search, think of the same grid that we talked about before, but instead of traveling through the grid one cell at a time, what we do over here is randomly pick cells from the grid and then run training jobs based on the hyperparameter values within that cell. Now, the number of cells that you pick is totally random, and it's also kind of an hyperparameter that you decide based upon your logic or your experience. Now, at the end of the random search, you would have executed n or k random jobs, and then you pick the job that gives you the best accuracy or best F1 score or whatever your objective metrics is. Obviously, as you can imagine, grid search is much faster than, random search is much faster than a grid search. But in most cases, it's been proven that random search actually performs very similar or as close as a grid search would. Obviously, it can never compete with a grid search because you are absolutely executing all possible combinations in the grid search. But when you're randomly picking up values from the grid and you end up picking a value that is the best option for that model, you may end up with the same performance as grid search. And random search is also more practical compared to a grid search because it gives you as a data scientist a lot of flexibility on how longer you want to, your hyperparameter optimization process to run. Now, SageMaker uses an intelligent form of hyperparameter tuning that's based on Bayesian search. Now, the way Bayesian search works is that it starts with a random search, but then after the first iteration or first round of hyperparameter tuning, it then feeds it to a Bayesian model, and it learns how the model is behaving with respect to its hyperparameters. So in the subsequent round, what it does, it uses that knowledge to pick, instead of randomly picking values, what it does, it uses that knowledge to pick values that are most likely to improve your objective metrics. Now, by default, SageMaker hyperparameter tuning does use random search, but does use Bayesian search, but you do have an option of also using random search with SageMaker hyperparameter tuning. With that, I will again hand it over back to Gal to cover the next few sections.
Awesome. Thank you. So thank you all for kind of listening. I know this is a lot of information, potentially for one of the last sessions in the conference, but just a little bit more. So kind of to summarize what we talked about so far in the session, we talked about core capabilities in SageMaker training for training your models, right? So ephemeral clusters where you pay for what you use, you get the flexibility of using different instance types, different cluster sizes. Then we talked about the libraries for distributed training that help you scale up your models, where you can use the SageMaker libraries or any library of your choosing. And then we talked about hyperparameter tuning, so being able to get the best accuracy possible by figuring out which hyperparameters work best for your use case. The final thing I want to talk about really quickly is the ability to do managed spot training on SageMaker. So when you kind of do large-scale training, and even at small scale, the cost can add up. So SageMaker lets you take advantage of spot instances, where you can use unused capacity from EC2 at a lower cost, but the workload has to be fault tolerant, which means that during the training, the instances can be taken away or interrupted, and the training will be paused. So one thing that's really important when you do spot training is that your model checkpoints during training. So at a certain frequency, let's say every 30 minutes, you save the model that you've trained so far. And then if the job gets interrupted, when it resumes again later, you can pick up the training from that last checkpoint so you don't lose the progress. And this slide shows how easy it is to get started with spot instances in SageMaker training. I add the parameter use spot instances, set it to true, and then I also set a max wait time, which is how long I'm willing to wait for the job to complete, because the instances might get interrupted. There might be some wait period kind of between the training, so I want to set that parameter something reasonable. But otherwise, I can get a pretty significant cost reduction just from this simple change. So over here, we have a few links for the product page for SageMaker that kind of explains all the capabilities that we talked about today, the documentation that helps you get started with those capabilities and how to use them. The examples on GitHub are really great, a really good selection of examples for different types of use cases in ML. And finally, the ML blogs, where there's some really great ones, such as a recent one on training 175 billion parameters for language models. So with that, I'll end by showing this slide with some information on the certification and training programs. And I think we have a bit of time for questions as well. And thank you again for listening.